Hello and welcome to Kwanang's Notes. So today we're going to be looking at the General Certificate of Education Advanced Level. We are going to be correcting the regional mock session for March 2022. And we're going to start with question 1 in these slides. So question 1 gives this differential equation x plus 1 dy dx plus y minus 2x equals to 0. And then Roman 1, we have to show that the third derivative multiplied by x plus 1 plus 3 times the second derivative is equals to 0. So in order to prove this, we move from what we know, what they have given us actually. So they said that x plus 1 dy dx plus y minus 2x is equals to 0. So this is what we have been given. So I'm going to expand this, so this is going to give me x dy over dx plus dy over dx plus y minus 2x is equals to 0. Sorry about that. So we're going to differentiate now implicitly this expression. So the first one we differentiate implicitly by product rule. So we're going to have x, we keep x constant, we differentiate it, we have the second derivative with respect to x, plus we keep the first derivative, we differentiate x, that's just going to give us dy over dx. And then we move on to this one, we differentiate, so we have d squared y over dx square, and then we derive these ones, we have dy over dx, and then moving on to these, we have negative 2 is equal to 0. We can't stop here because we don't have the derivative appearing yet, so we have to move on with the derivation. So we calculate the derivative for this second expression again by product rule. So we keep x constant, we derive this, that's going to give us the third, I'm not sure why I want to write an x here. So this is the third derivative with respect to x, plus now keep x constant, dy d square y over dx constant. So differentiating x, that's just giving me constant. So plus differentiating this one, we have the second derivative, plus deriving this, we have the third derivative, plus the second derivative for this one, and this two is just going to give us a constant, so this is 0. Now we have guys that are common here, so we have this and this, which are friends, so we have x plus 1 that can be factored out, so we have the third derivative. Okay, so plus, so we have 3 times the second derivative appearing, so this is 3 second derivative, and this is equal to 0. So we came up with what they were asking for. So in Roman 2, they tell us that given also that y is equals to half and x equals to 1, that we should show the solution of the differential equation as series of ascending powers of x minus 1, up to and including the term in x minus 1 to the power 3 is this. Okay, so this is a special case where the solution to a differential equation is expressed as a power series, and we know that the solution can be written in the form y is equal to the sum from n equals to 0 to infinity of a sub n x to the power n. But we are not interested in what's happening around the point x equals to 0, but we're interested in the power series around the point x equals to 1. So we want something like that will look like y is equal to the sum from n equals to 0 to infinity a sub n x minus 1 to the power n. Sorry about this. Okay, so how are we going to do this? Okay, we know this is an expression that depends on n, so we can derive it as well. So we can have the first derivative that can be written as such. So the sum, now the first derivative is going to start from 1. You can check from your notes. If we derive once, we'll lose a term. So from n equals to 1 to infinity, we'll bring down the n, a to the power n, a to the power a sub n x minus 1 to the power n minus 1. Okay, so you agree with me that the second derivative is just going to be starting from 2 to infinity, and I'll bring down the n minus 1, a sub n x minus 1 to the power n minus 2, and that the third derivative will be starting from 3 to infinity, n minus 1, I bring down the n minus 2, a sub n x minus 1 to the power n minus 3. So this is what we know. Okay, now we have the equation we've just proven from the previous slide, and he said that x plus 1 times the third derivative plus 3 times the second derivative was equal to 0. So this is what we know. So what we're going to do is that we're going to take these expressions and plug them in here. So we're going to plug them in here. Okay, so doing that, we have x plus 1. So the third derivative is this one over here. So we plug in all that expression, so it's going to give us the sum from n equals to 3 to infinity n minus 1, n minus 2, a sub n x minus 1 to the power n minus 3. Okay, so this is this for the third derivative. Now plus 3 times the second derivative. This is the expression over here. So the sum from n equals to n equals to 2 to infinity n minus 1 a sub n x minus 1 to the power n minus 2. Now we're done. Okay, so when we're here, most of the time the next step we want to do is that we want to transform all these things to the power n minus 2 and minus 3 to the power n. We want things in the line of x to the power x minus 1 to the power n. So how do we make these things to the power n? That's the next thing we're going to do. So notice there's a trick here. There's x plus 1 that is multiplying this expression, and I can't get it in here to multiply this x minus 1 to simplify the n because the bases are different. So what I'm going to ask myself is that how can I build x minus 1 from x plus 1. And you can agree with me that x plus 1 is just x minus 1 plus 2. So it means I can rewrite this x plus 1 as x minus 1 plus 2, and then all this is going to multiply this expression. Like so. So plus 3 So once I've done that, I have to distribute now this expression. So I'll do this. So I have x minus 1 into the sum n minus 1, sorry, n minus 2 an. So now it be plus 2, this sum, that same sum, to infinity, n minus 1, n minus 2, a sub n, x minus 1, n minus 3, like so, and then plus 3, the sum, n equals to 2 to infinity, n minus 1, a sub n, x minus 1 to the power n minus 2. So once I've done this now, I have a good deal. So I can let this guy in, so that this expression now will become the sum from n equals to 3 to infinity. Now this is going to give me n minus 1, n minus 2, a sub n. Now x minus 1 to the power what? This is going to be to the power 1, so this is n minus 3 plus 1. This is n minus 2 plus 2, the sum from n equals to 3 to infinity, n minus 1, n minus 2, an, x minus 1, n minus 3 plus 3, n equals to 2 to infinity, n minus 1, an, x minus 1 to the power n minus 2. So once I've done this now, I have to make these powers now to the power n. So to be able to do this here, I have to substitute n by n plus 2, so that I'll have x minus 1 to the power n for this one. Now for this expression here, I'm going to get n as what? N plus 3. And for this one, I'm going to get n as n plus 2. Is that okay? So having done that, I move on to the next slide to have more room. So I copy what I had for the previous side. So I had the sum from n equals to 3 to infinity. So let me just come back to the previous side. So I have n minus 1, n minus 2, an, x minus 1. I have n minus 1, n minus 2, an, x minus 1 to the power n minus 2. Okay, plus 2 so plus 2, the sum, n equals to 3, n minus 1, n minus 2, an x minus 1 to the power n minus 3, then plus, sorry about that, plus 3, the sum, n equals 2 to infinity, n minus 1, an x minus 1, so n to the power n minus 2. Okay, so here we have to replace n plus 2. Here we have n plus 3. Here we have n plus 2. So if we do that, this is going to give me the sum. Now n plus 2 now, so I'm going to have n plus 2 is equal to 3. So n now be equals to 1. So we'll be leaving from 1 to infinity. Now n is n plus 3 plus 2, sorry, so n plus 2 into n plus 2 minus 1, n plus 1, n plus 2, this is n, an plus 2, x minus 1 to the power, oh, sorry about that, this is going to give me to the power n, plus, okay, plus, not sure why the plus, not plus, 2, the sum. Now replace n by n plus 3, so n is going to start from 0 to infinity, so n plus 3, n plus 3 minus 1, n plus 2, and this is n plus 1, n plus 3, x minus 1 to the power n, plus, okay, this is going to give me 3, the sum. I replace n by n plus 2, so n is going to start from 0 to infinity, n plus 2, n plus 2 minus 1, n plus 1, an plus 2, x minus 1 to the power n, just to the power n. Okay, we're done now. We have put everything to the power n. That was the first step, and the next thing we're going to do, we're going to get all the starting points to the highest starting point, that is to n equals to 1. And that what that means is that these two expressions over here, I'm going to let them start at 1. So I'm going to take out the 0th term, so for this one and this one. So this, I'm going to rewrite it as such. I'll not change anything for this. So n plus 2 into n plus 1 into n, an plus 2, x minus, sorry, x minus 1 to the power n. Now I'm going to take the 0th term for this, so this will give me plus 2 into, so I'll put 0 here for n equals to 0, so I get 2 times 3 times 2 for this times 1 times a 3, x minus 1 to the power 0 is just 0, so that's 0. Then I'll do the same for this, So this will give me 3 into 0, 2. So this is 2. I'll put 0 there, I have 1. So a 2 x minus 1 to the power 0 is just 0. So plus the 2. Now starting from 1 to infinity of n plus 3, n plus 2, n plus 1, a, n plus 3, x, so plus this term 3, now starting from 1 to infinity, n plus 2. Not sure why this is disturbing today. N plus 2, n plus 1, a n plus 2, I'm sorry this takes long, but this is how these problems look like. So you just have to be very careful and persistent and quiet and calm while doing them. Okay. So we're almost there. So I have two constants here. So this is 2 times 3 times 2. It's 6 times 2, 12. So this is 12 a3 plus 6 a2 plus, now that the starting points are the same, so I can factor out n equals to 1 to infinity. Okay, and then I'm going to write what is inside the factor and x to the minus 1 to the power n at the end. So I'm going to open a big bracket. I'll write this one first, so n plus 2 into n plus 1 into n, a n plus 2, so plus 2 into n plus 3 into n plus 2 into n plus 1, a n plus 3. Sorry about that. So plus, so plus 3 into n plus 2 into n plus 1, a n plus 2, and all these times x minus 1 to the power n. So this is equal to 0. Everywhere here is equal to 0. I'm sorry I didn't write it. All these lines are equal to 0. Even for the previous slide, this should be equal to 0. Okay. Alright. Okay, so now if this is equal to 0, it means this over here amounts to 0, and all these things inside the coefficient amounts to 0 as well. So it means that from there we have 12a3 is equal to 6a2 minus, actually, or let me just write it as 12a3 plus 6a2 is equals to 0. So this will mean that a3 is negative a2 over 2. Okay, and the other expression we have is that n plus 2 n n plus 2, n plus 1, n an plus 2 plus 2 an plus 3 plus 3 an plus 2 is equal to 0. So this, we see like terms that can be cancelled from this already. So we have this, that goes away. So I have an plus 2 is common. So I have an plus 2 into n plus 3. So plus 2 n plus 3 into an plus 3 is equals to 0. So this is to say an plus 3 is equal to, if we bring this one the other way, so this will give me negative an plus 2 over 2. So this is the expression for an plus 3. So we're almost there. Knowing that our a0 is equal to half. Okay, so if we have, for example, n equals to 0 in this expression over here, we get that a3 is going to be negative a2 over 2, that we already know. So if n maybe is let's take n as negative 2, for example. So that's going to help us compute a1, and that will be negative a0 over 2. That will be negative half over 2. That's negative 1 over 4. So if we take maybe n as minus 1, that will help us compute a2, which will just be negative a1 over 2, which is negative times negative 1/4. That gives me 1 over 8. And of course, a3 is just negative a2 over 2. And that gives me negative half times 1 over 8. That gives me negative 1 over 16. So we're done. We found our coefficient, so it means our y can be written as the sum from n equals to 0 to infinity of a sub n x minus 1 to the power n. So we can sum this up to n equals to 3. So if we do that, we're going to have a0, because x minus n, so let me just write it out, x minus 1 to the power 0 plus a1 x minus 1 to the power 1, which is just x minus 1, plus a2 x minus 1 to the power 2 plus a3 x minus 1 to the power 3. So we have these coefficients. a0 is half, a1 we just saw it, a1 is negative 1/4, So that will give me minus x minus 1 over 4 plus a2, we just saw is 1 over 8. So that will give me x minus 1 squared over 8 minus a3 is negative 1 over 16, so that will give us minus over 16. So we are done showing the example. So the next question, they're asking us to find the value of y when x equals to 0.8. This one is very straightforward. So we know from the previous slide that y is equals to half minus x minus 1 over 4 plus x minus 1 to the power 2 over 8 minus x minus 1 to the power 3 over 16. So we're just going to substitute x as 0.8, so have y is equals to half minus 0.8 minus 1 over 4 plus 0.8 minus 1 square over 8 minus 0.8 minus 1 cube over 16. So this gives me 0.5 minus sorry, minus 0.2 over 4 minus 0.2 square over 8 minus 0.2 cube over 8. So that gives me 0.5. So I'll do this on the calculator very quickly. So doing this on the calculator very quickly. So this gives me minus 0. So 0.05. So plus 0.005 minus, that's just going to give me a plus this is 16, so 0.0005. So this is going to give me as final answer 0.5 plus 0.05 plus 0.005 plus 0.0005. So this gave me 0.5555. Okay. So in this slide, we're asked to use the approximation 2h dy dx is equals to yn plus 1 minus yn and the step length of 0.2 to find the value of y when x equals 1.4. This pretty much looks like Euler's method, but we're going to use Euler's rule, but we're going to use what they gave us actually. So we know from the very first expression given us that x plus 1 dy over dx plus y. Oh my god, it's trouble writing this plus plus y minus 2x is equals to 0. So this will mean that dy, not sure why this is, dy over dx is, making it subject to the formula, 2x minus y on x plus 1. Okay, so this is this. So we have from this approximation that y n plus 1 is yn plus 2h dy over dx. So we start our algorithm. So we start with x0 we know is 1 and y0 is 0.5, and then we're going to increment this because we said the step length is 0.2, so it means that the next value for x is going to be 1.2, and then we'll increment this by 1.2 to get 1.4, and we find the corresponding y's, that's y1 and y2 for that. So straightforward, if you want to find y1, it's just happening for n equals to 0 for this expression. So y1 is going to be y0 plus 2 times the step length times the derivative happening at x0 y0. Okay, that's the points before. So this is going to be this is so the derivative at x0 y0 is going to be 2 times 1 minus 0.5 divided by 2. So this gives me roughly, let me do down the calculator roughly. So I have 1.5 divided by 2, 0.75. So this gives me 0.5 plus 2 times 0.2 times 0.75, and this will give me 0.8. So this is my y1. So moving on to y2. y2 is going to be y1 plus 2h, the derivative of y with respect to x at x1 y1. So we still do what derivative is at x1 y1. We'll find out what the derivative is. So this is going to be 2. Now x1 is 1.2, y1 is 0.8 divided by 2.2. So this will give me 0.72. So if I have this, substitute right in here. So I have 0.8 plus 2 into 0.2 into 0.72, and that would give me 1.0909, and this is what we're looking at. So this is an approximate value for y when x equals to 1.4. So this last question asks us to evaluate the integral of y dx under the interval 1.4 using Simpson's rule with 3 ordinates. So really quickly we'll call Simpson's rule. So Simpson's rule says the integral from a to b of a function f of x, okay, f of x dx, okay, can be approximated to some h over 3 into f of x0 plus, then we start alternating between 4 and 2. You should get this from your formula booklet. This is not, no need to retain these, I think. So plus 2 f of x2 plus and you just alternate between 2 and negative 2 and 4 and 2, sorry, until the last term you will be just like the first term. So f of xn will not multiply anything, so like this. And so to calculate h, we say it's just b minus a over n. So for this example, it's straightforward. We have to calculate we have to figure out the integral from 1 to 1.4 of y dx. So it means that our h we're looking at here is 1.4 minus 1 over 3. That gives me 0.1333. Okay, so it means that we have 3 ordinates, so I have to leave from 1 to 1.4. So in between here I have 1 plus this, so it's 1 point, sorry, so it is 1.1333. Then I have 1.2667. Okay, so this integral, the integral from 1 to 1.4 of y dx is just going to be 0.1333 over sorry, over 3 y at 1 plus 4 times y at 1.3333 plus 2 times y at 1.266, okay, plus y at 1.4. So basically we have to calculate all these coefficients. Y at 1 we already know, this is going to be 0.5, y at 1.333. For the sake of time, I've calculated this, so it's just obtained by substituting. So you will do this on your own when you have time. So this is 0.4688. So y of 1.267 actually is 0.4412, and y of 1.4 done by plugging is 0.416. So it means that our integral y dx is 0.1333 divided by 3 into 0.5 plus 4 times 0.4688 sorry, plus 2 times 0.4412 plus 0.416. Okay, so this will give me the integral from 1 to 1.4 y dx approximately equal to 0.1632. So this is it for the first question under the regional mark. So the other video for the question 2 is going to come out very soon, so stay tuned. Bye.